Welcome to another video in the Basic Audio Engineering live mixing course. So this video is all about volume and sound pressure level. I will basically talk you through where does actually decibel come from, and I will also give you a lot of other knowledge about how we basically have to use the decibel scale and where it is applied also in practice. So volume basically is measured to be very accurate in Pascal. So when there is a sound, like a sound wave in the air, there is air pressure. We talked about that in earlier videos too. And depending on the air pressure, the sound we hear, it's louder or more quiet. And basically this air pressure, so the volume of the sound, is measured in Pascal. The human hearing threshold, so the basically most quiet sound which we can hear as humans, is 0.000, did I say enough zeros now? It's like 4 zeros to Pascal. That's basically the sound a feather slowly dropping on the floor makes when at the point when it hits the floor. So that's the most quiet sound humans can hear. And then there is a threshold of pain. So the loudest sound before it hurts really our ear is 100 Pascal. That's basically the point where that's basically the point where when we stand in front of an airplane engine, an airplane just starting, that's basically the sound we would hear. So just pretty very loud sound. So there is now one big issue with this Pascal scale. The thing is, the most quiet sound, 0.00002 Pascal, is there's like lots of zeros, and it increases pretty fast. So the first like proper sounds we can hear is still in this zero range. So we always have to deal with like lots of zeros, and then at some point we get into the 1 to 10 pascals, and at some points to 1 to 100 pascals. So this scale is not really nice to work with, because it starts at this very tiny small little number. So there at some point came someone, and his name was Bell, and he decided to do a different scale, which is called decibel. So dezi just stands for 10, and Bell is his name. So that's how decibel was introduced. And what I now do is I just walk you through a step-by-step process on how to get from the sound pressure level, like the physical pressure level, which is measured in Pascal, to the decibel. And this process doesn't really make sense at first sight. You just basically have to follow it to get to the new, you basically just have to follow the calculation. So on this slide you can see the process of doing this calculation. So I just take one example here and I show you on this example how it works. So we have an airplane engine. We have an airplane engine, and the air pressure is 100 Pascal, so the max pressure we can basically sustain as humans. It's 100 Pascal, and we now also know already that the threshold of hearing, so basically I call it P0, so the lowest, the most quiet sound we can hear, we know that it is 4 times 0.2 Pascal. So what do we do now? The first thing we do to get to decibel is calculating the ratio from the engine and the most quiet sound we can hear. So we use P engine and divide it by P0. So 100 Pascal divided by 0.00002 is 5 million, which is 10 to the 6.6987. We have to basically change it into an exponent, or into the 10th exponent, because we continue working with this number. So if you would calculate 10 to 6.6987, you would get exactly 5 million. So what we now do as a first step is we basically take this exponent 6.6987 and continue working with this one. So we take it and we double these results. So we double 6.69 so that we get 13.3974. And this thing here now is the bell unit. This is basically already it. So we just have to add the dezi now. We don't speak in bell, but we speak in decibel, so in tenth bells. And to get there, we basically just calculate it times 10. So 13.3974 times 10 is 133.974. And this is basically the volume in decibel now. And this is what we also see on every mixer, in every mixing console, and lots of other places as well. So yeah, basically what you do is really just take the volume in Pascal, take the exponent, double it, and calculate it times 10. That's basically it. So the question now we could ask is how many decibel we get when the volume doubles. So when the volume doubles, this basically means we have double the amount of Pascal, right? So yeah, we have some certain volume, doesn't matter what it is, in decibel and or in Pascal, and we want to double that volume, so we take the pressure level in Pascal and double it. So what we do, we take two volumes to just show you this now, and these volumes are P1 and P2, and let's say P1 now is double the volume from P2. So P2 could be 10 Pascal, P1 would be 20 Pascal. So this means if P1 is double than P2, if we divide P1 by P2, we always get 2, right? Like 20 divided by 10 is always 2, like double. As P1 is double the size of P2, the result will always be 2. And if we again write it in 10 with 10 and exponents, we would get 10 to the 0.3. So basically the ratio between the two is 10 to the 0.3. So again, we can now take this volume difference we got here in Pascal, and we can change it to what the volume difference is in decibel. So we do that again. We take the exponent 0.3 and do the exactly same process as before. We calculate it times 2 to get 0.6, and we calculate times 10 to get 6 decibel. So this calculation here now proves that basically when we double the volume, we basically increase the volume in decibel by 6 decibel. So that's a quite crucial point to understand. The volume is not, if you double the volume, it's not double the decibel, it's only 6 decibel more, which doubles the volume already. This calculation might have been a little faster, just watch the video a few times until you recognize or understand how these calculations really work. But the important thing to understand and also to remember is that whenever we double the volume, it's only 6 decibel which we have to add in the decibel scale, which yeah, might be quite surprising, as as you might have been thinking we just double the decibel to double the volume of the sound, which is not true as we see that here. So I want just to give you now a little bit of intuition how loud, how many decibels different sounds we hear every day have. As I told you already, hearing thresholds is in the end 0 decibel. When you are in a quiet room, no one is talking, but still there is some background noise. There's always some background noise. You will already have 10 up from 10 to 30, something in between 10 and 30 decibels in that room. When someone whispers to you, it's 30 to 40 decibels already. And people just talking with each other, as I do with you now, like a dialogue, that would then be 60 decibel. And then it goes up. Traffic noises is like 70 to 90. And then that's probably interesting for us. A concert is 90 to 110 decibels. So I will later on talk about what level, what volume should concerts be like. Yeah, and then it goes up, like until we get to the jet fighter or the airplane engine, which is approximately 130 dB. Some other guy, he was called Mr. Phone, did another scale than decibel. He did the phone scale, and the reason he did it is that our ear reacts different to different frequencies. So there is frequencies which we think they're louder, even though it's the same amount of decibel, and there is frequencies which we think they're more quiet, but it's actually still the same level of decibel. So Phone, Mr. Phone, he did another like a phone scale. And what I want you to understand here is just one thing basically. So I just take one example. Let's use 20 phone here. So whatever 20 phone exactly means, it's just a certain level of volume. And this curve here now shows us one important thing. So we have on the y-axis we have the level of sound in decibel, and we have the frequency. And this line here basically means that if we have a sound which is 20 phone, we hear it along this line, our ear hears it at the exactly same level. So what does that mean? That means that our ear basically, if the sound has a frequency of something a bit above 2 kilohertz, our ear thinks it's louder than when the sound is just, let's say, 0.1 kilohertz, so 100 hertz. So that means higher frequency, especially in this range, our ear recognizes them much faster. And this we should be aware of, that we hear frequencies in that range much louder and much faster, and probably we should consider that when we do the mix, that it doesn't hurt our ear. We often have to decrease a little bit the frequencies in that range. That's also the reason why when we like speak, we understand people the best if the volume is loud enough, around 2 to 5 kilohertz. So if someone is not, if you do a mix and you cannot understand the person talking well, you could probably try to rise around these frequencies a little bit, the level, and then people can understand the person better, because our ear, our mind, our brain is basically trained to understand what a person says when like around these frequencies, because we hear them the best. So that's just the phone, that's just this phone scale compared to the decibel scale. And just be aware that we basically as humans don't really hear well the low frequencies, but the higher we go, the faster and the better we hear the frequencies. That also has an influence on the evaluated sound pressure level. So there is regulations, often by law, how loud a certain event is allowed to be, and the regulations done by law are normally use different curves. So the country I come from, they often use this A scale here, and that means that this scale basically reflects the phone scale. So what this scale says is that when you do a show, like an event, a concert, you are allowed to go much louder at low frequencies, but higher frequencies are taken into account much more. So you have to make sure the high frequencies are not going over a certain threshold. So these regulations basically take the phone scale also into account and make sure that that basically the level at every frequency is not going over a certain threshold. So another quick thing I want to talk about is what is happening when the sound is traveling through the air. Of course, when the sound travels through the air, it also loses energy the further it travels. And what we can basically say is that whenever we double the distance, the sound pressure level also like halves. It loses half of its energy. So at a distance of 2 meters, we lose 6 decibel already. So the sound pressure level is already half than it was at its source, at the speaker. Then when we add 1 meter, we have minus 10 decibel. So the sound level dropped to minus 10 from its original source at the speaker. At a distance of 5 meters, we are at minus 14 and so on. So we just have, it's important to know that when the sound travels through the air, it loses also energy. I mean, it's not only losing energy when it hits a wall and gets absorbed or whatever. It also loses energy just by traveling through the air. That's why we don't hear sounds kilometers away. So just be aware a little bit of these distances and know how I think it's nice to know how the sound level decreases over distance also. And the last thing I would like to mention is coherent signals. So when you have 2 speakers at the exactly same place and both of the speakers send the exactly same signal, then you basically get waves which overlay 100%. So what happens when you have 2 sound waves exactly the same is they are summed up. So the pressure level in Pascal, it doubles, which means that you get 6 plus dB. So basically double the sound pressure level. So that was now a lot of content within a short time. Probably you would watch this video once more to just understand the content. It's, I think, not really important to know exactly how to do all these calculations, but I think it's important to know that, at least to know that if the sound is double as loud as before, it's an increase of 6 decibel. That's at least you should remember, and also that humans hear around 2 to 5 kilohertz the fastest, so around 2 to 5 kilohertz our ear gets heard the fastest. Basically, it's the most sensitive in that area. All right, thank you for watching the video, and I will see you soon in the next video.